Hi, in this video we're going to continue our study of sequences by looking at limits of sequences. So we're going to try to relate as much as we can sequences and their limits to functions and their limits. So to do that, let's start by looking at the sequence 1 over n squared. Remember, when we talk about sequences and their limits, just like with functions, we don't really care what the first few values are. We just care about the tail end. So let's go ahead and look at some values of the sequence. So we have 1 over 1, 1 over 4, 1 over 9, 1/16, 1/25, and so on. Maybe go out 1 over 100. This is for n is equal to 10, and so on. And if we were to graph this, we would see that we start at 1 and then go to 1/4, 1/9, 1/16, and so on. And we continue all the way down, and we're getting closer and closer to 0, but we're never quite hitting it. So it would make sense to say that the limit as n approaches infinity of the sequence an, which is the limit in our case as n approaches infinity of 1 over n squared, is equal to 0. And this is going to be the motivator for the limit of a sequence. So let's actually define what the limit of a sequence is. So definition, and this is called the n epsilon definition of a sequential limit. Okay. So we say that the limit as n approaches infinity of an is equal to L if there is or there exists, this backwards e means there exists, a natural number n, we'll call it big N, such that if we take an and subtract L from it, this is going to be less than epsilon for every, and we use an upside down a for every, little n bigger than this big N. So after we hit a certain point, everything is going to be less than some epsilon. And like I said before, we're caring about that tail end. We don't really care about the first 2, 3, 4, 100, 1,000, 1,000,000 terms. We just really care about what happens towards the very end of our sequence as we get really far out, just like a functional limit. And what we're going to do, since all of our limits actually take place at infinity for sequences, we're just going to write the limit of an instead of the limit as n approaches infinity. We will, if necessary, if things are unclear, but for the most part, we're just going to write the limit of an. Now, the limit of an is equal to infinity if there exists a real number m, or if for every real number m that is greater than 0. So if you give me any positive number, then there exists a big N in the natural numbers. So there is a point in our sequence where an is greater than m for every n greater than n. Okay, so this says that give me any positive real number at some point in time in the sequence. I'm going to start being above that. And finally, for our definition of a limit, we say that the limit is equal to negative infinity if for every m less than 0, so no matter how negative you get this number, there exists a certain point in our set or in our sequence such that an is less than m for every n greater than n. So everything past that point is going to be less than some negative number. And this is the definition of a sequential limit, the formal definition. But let's get a working definition. So a working definition. Okay, so the limit of an is equal to L if an gets arbitrarily close to L for large N. And it needs to get close to only L for large N. So let's say to only L for large N. And the limit is equal to infinity if an increases without bound after a certain point, so as n goes to infinity. And the same thing for the limit as an is equal to negative infinity. So this is, it decreases without bound as n goes to infinity. And this is, the limit is equal to negative infinity. So how do we find limits of sequences? So finding the limits of a sequence. Well, there's a really easy procedure, and we actually just bring it over to a function and evaluate the functional limit. So we're going to replace an with f of x. And then we're going to take the limit as x goes to infinity of f of x, and the limit as x goes to infinity of f of x is equal to the limit as n goes to infinity of a sub n. Note here that it doesn't really make sense to take the limit as x approaches negative infinity of f of x, because an goes to infinity. So it starts with a1, then goes 2, 3, 4, and over to infinity. It doesn't go backwards, so it wouldn't really make sense to talk about the limit as we approach negative infinity of f of x. So let's take a look at an example. We want to know the limit of this function, of this sequence, 3n plus 3 over negative 7 plus 2n. And now looking at this, we're just going to replace with f of x. So we're just going to take the limit as x goes to infinity of 3x plus 3 over negative 7 plus 2x. And we can just use L'Hopital's rule on this, or we can divide everything by x, or we can use from college algebra or some previous algebra class the ratios, since they both have a term of x to the first. There are a bunch of different ways we can evaluate this limit, but let's use L'Hopital's as a refresher. Remember, this is the same as the limit as x goes to infinity of the derivative of the top over the derivative of the bottom. And so the limit of 3 halves is 3 halves. And this tells us that the limit of our sequence an is equal to 3 halves. Now let's look at some properties of limits. So if we have an and bn be two convergent sequences, we'll say that the limit of an is equal to a and the limit of bn is equal to b. Then the limit of an plus bn is equal to a plus b. We can split up the limit over addition. We can also split up the limit with a constant. We can take that constant and pull it on the outside of the limit. We can also multiply limits. So the limit of an bn is equal to the limit of an times the limit of bn. And if we have the limit of an to the p, we can just pull that exponent out, and that's the limit of an to the p, whenever an is positive or 0. Next we have the squeeze theorem. So the squeeze theorem says that if there is a certain point such that a sequence is between two sequences that converge to the same number, then that one in the middle also converges and has the same limit. Remember, this is just like the squeeze theorem from functional theorems in our functional calculus. Okay, the next few are a little bit more esoteric, and we might not necessarily remember these from calculus. So if the limit of the absolute value of a sequence, or the limit of the absolute value of an is equal to 0, then the limit of an is 0. So if it's positive, or if its absolute value converges, then it converges itself. Next is a property about exponentials. So if I have a number to the nth power, and that's my sequence, then that converges if the thing that we're raising to the power is between 0 and 1. And if it's 1, it also converges. And that goes into our next property of limits, that the limit of Rn is equal to 1 if r is equal to 1, and it's equal to 0 if it's between -1 and 1, non-inclusive. Now if it is -1, we'll see in a quick example that it does not converge because there are two different numbers that it bounces between. Our final limit property is that if the limit of a2n is equal to L and the limit of a2n plus 1 is equal to L, then an converges and the limit is equal to L. And we can just sum this up by saying if the even parts of the sequence converge and the odd parts of the sequence converge, and they go to the same number, then the whole thing has to go to that number. It makes a little bit more sense if you think of it as every other one converges to one number, and then we fill in the other ones, the other gaps also converge to the same number. So let's take a look at the example. We want to determine the convergence. So convergence of the sequence -1 to the n, as n goes from 0 to infinity. So we just want to know, does the limit of -1 to the n exist? And if we look at using property 9, so let's just pull that up, the limit of a2n is equal to the limit of 1, which is 1. So that exists. But then we look at the limit of a2n plus 1, and that's going to be the limit of -1, and that's -1. Since these don't coincide, so they're not equal, that tells us that this limit of -1 to the n diverges. Remember, just like back with calculus 1 and functions, if a sequence doesn't converge, then we say that it diverges. For our next example, let's take a look at the sequence -1 to the n minus 2 times n squared over 4 plus n cubed. Now we're going to use the fact that if an, the absolute value, converges, then so does an. Right? So if the sequence of absolute values converges, then the sequence itself converges. So looking at the absolute value of an, that's just n squared over 4 plus n cubed. And now we can just evaluate this integral, or, sorry, I'm still in integral mode. We can just evaluate this limit by converting it to a function of x. So we're just going to take a look at the limit as x goes to infinity of f of x, which is x squared over x cubed plus 4. And now this is infinity over infinity, so we can use L'Hopital's rule, and we get 2x over 3x squared times 2, so we can just make that a 6. And then we can reduce this to 1 over 3x, and we still take the limit, so let's go ahead and put those limits in there. So we're looking at the limit as x goes to infinity, and we just cleaned this up. We didn't even use L'Hopital's rule. So this is just the limit as x goes to infinity of 1 over 3x, which is going to be 0. So for our final example, let's take a look at e to the 5n over 3 minus e to the 2n as n goes from 1 to infinity. So let's just take a look. We'll get f of x equals e to the 5x over 3 minus e to the 2x. And we'll take the limit as x goes to infinity of f of x. Now, if we plug that in, we immediately get infinity over negative infinity. So we can use L'Hopital's rule on this. And using L'Hopital's rule, we get 5e to the 5x over negative 2e to the 2x. And now we can clean this up, and we get negative 5 halves e to the 3x. And taking the limit as x goes to infinity of negative 5 halves e to the 2x, we get negative infinity. And this tells us that our sequence diverges. And that concludes our talk about the limits of sequences for now. Next time, we'll talk about increasing, decreasing functions. We'll talk about bounded functions, and we'll talk about how being bounded and increasing or decreasing actually determines if a function is convergent or divergent. So, as always, if you have any questions, comments, or concerns, leave them down in the comments below, and I will get back to you. Thanks for watching.